So, good day, everyone. So, let us continue our discussion on emerging technologies, especially on geographic information system. Okay, so this is the outline of our topic for this week. No? We'll discuss the GIS data, types of GIS data, the examples of GIS data sources, remote sensing, applications of remote sensing, what is GPS and GIS integrations. We will define LiDAR and aerial photography, OpenStreetMap and crowdsourced data, methods of data acquisition, and factors that affects the data quality in GIS. So basically, GIS data again refers to the information that is spatially referenced, allowing it to be associated with specific geographic locations, including both the attributes and spatial coordinates no, of features on the Earth's surface. For example, the vector data and the raster data. Again, GIS data refers to the information that is spatially referenced. No, so that's the GIS data. So again, here are the two types of GIS data: the vector and the raster. When we say vector data, we have here the points, the lines, and the polygons. Point data, GPS coordinates of landmarks. Line data, these are the roads, rivers, and pipelines. The polygon data, it's the political boundaries and land parcels or land areas. No? On the other hand, raster data, these are the satellite imagery of the Earth and elevation models. Okay. So these are the common data sources of GIS. We have census data, satellite imagery, topographic maps, geospatial surveys, and publicly contributed data. Ano ba itong census data na to? So these are demographic informations that have been collected by various government agencies, for example, NAMRIA, MGB, DRRM, DLG, no, and other agencies that require GIS data to perform their responsibilities. Okay, so that's census data. These are collected by government agencies. Second one is satellite imagery. Ano naman ito? So these are images that obtained from Earth observation satellites. So these are again mga satellites na nag-orbit around the Earth. No? Meron silang kinukuha mga imagery using their satellites. Third one is topographic maps. Itong topographic maps na to, these are detailed maps illustrating surface features. For example, a rolling mountainous area, idle area, forest area, yung ano tawag ito? Bathymetric map. No? So those are topographic maps. No? Detailed maps illustrating the surfaces features. Okay, kung mabundok, kung rolling, kung mountainous, and those are the sample of surface features. Fourth one is geospatial surveys. These are ground-based surveys using GPS technology. So these are field surveys, no, on the ground data collection or gathering. They use GPS technology or the global positioning system technology, through ground surveys. So these are geospatial surveys. And the last one is publicly contributed data. These are data from platforms like OpenStreetMap, Google Earth, Mapbox. No? So those are contributed data. You know, these data come from volunteers. No? So these are the 5GIS data sources: census from the government, satellite imagery from satellites, topographic maps that illustrate surface features, geospatial surveys using GPS, and publicly contributed data coming from volunteers. So now let us discuss remote sensing. this satellite imagery and aerial photography. When we say remote sensing, no, it involves the collection of information about an object or phenomenon from a distance. No? Medyo malayo or malayo siya. Typically, through the use of satellites, aircraft, or other sensor technologies, it enables the capture of data without direct physical contact with the subject. No? Ang purpose naman na to ng remote sensing is to gather data on Earth's surface and atmosphere for analysis and monitoring. Okay? So example nga ng remote sensing natin is satellite imagery that captures detailed images of the surface of the Earth, and aerial photography that gathers high resolution, takes high resolution photograph taken from an aircraft. No? So again, remote sensing involves the collection of information about a phenomenon from a distance. No? Typically, they use satellites, aircraft, or other sensor technologies. It enables the capture of data without direct physical contact with the subject. So, to give you more idea what remote sensing is, let us watch these two videos. Okay?
Remote sensing is observing a medium, a process, some phenomenon without ever coming in direct contact with that phenomenon. So unlike a lab experiment or where you go to a place and make an in situ measurement or actually touching the medium, remote sensing is observing it remotely from a distance. And this actually provides a different kind of perspective on things. When you're part of your medium, you're part of your experiment, you're part of the experience, you get one perspective that's crucial. You get a very different one when you're removed from it, when you're looking from space, when you're looking from 400 or 500 miles away, or in some cases 20,000 miles away. We can start up close, we can stand in a place and look at it, and we can zoom out, and all of a sudden it takes on new meaning. The trees are part of a broader system that sit on a landmass that is a country, that's part of a continent, that sits in an ocean. And as we step back further and further and look at those same trees, we may not see the leaves from far away, but we see the trees and how they fit into a broader Earth system, the clouds that surround them, the ice that's far north or far south of them, the oceans that really are affecting the climate that is causing those trees to grow.
You know, satellites are really the best way to measure the effects of climate change, because just one person on the ground in one place, it's very difficult to say if what you see in front of you is due to climate change or due to some local phenomena or is just the weather. And from space we can look at the whole Earth and we can integrate these observations of the whole Earth and really make a better assessment about what's causing these changes and what their long-term prognosis is.
A decade ago, the Earth observing system was beginning to be put in place. A series of satellites designed to observe the Earth, take a snapshot of the Earth over a period of years to understand its behavior. Well, to date, there are 14 Earth observing satellites orbiting right now. And of those 14, 13 are past their design life. They're living on borrowed time and could go away at any moment.
I think funding for these satellite missions is very much threatened right now. There doesn't seem to be a lot of support in political circles right now for these missions, and so that's something that as scientists we're trying to do, is to educate people about why these are so important. Like I said, the GRACE mission has been really, in my opinion, one of the best tools we have for measuring the impacts of climate change on the Earth. It tells us where the water is going, and that's, you know, when we talk about climate change, everybody thinks about the temperature, but it's really the water availability that's going to be the big impactor. And so we'll be able to tell with GRACE, you know, where we're losing water, where there's going to be prolonged droughts, where there's going to be more flooding, where the ice is melting. It's just this wonderful tool, and now we're going to lose this tool for probably 2 to 3 years. And you know, it's really unfortunate that we've kind of taken away one of our eyes in the sky.
The Earth is changing in ways that will affect our lives. And just as we're realizing how and why these changes are occurring, our ability to understand them is diminishing. And frankly, our future, our success in the future as a society really depends, is intimately linked to our ability to anticipate what's coming.
If you wanted to know the temperature of the ocean, how would you take it? Would you be able to do it in only one spot, or could you find a way to do it across the entire ocean? What if you wanted to see how an area was changing over time? Could you track how the shape of the coastline changes due to erosion, rising sea level, or a strong storm? Or have you wondered where animals like whales and sea turtles spend their time in an ocean? Do they move from area to area based on the season or changing ocean conditions? NOAA, the National Oceanic and Atmospheric Administration, works to answer these questions and more. One way is by using a technique called remote sensing. Remote sensing is the science of obtaining information about an object or an area from a distance. Typically, NOAA uses sensors on board a satellite or aircraft to collect this information. These sensors can be passive or active. Passive sensors collect information about energy that is reflected or emitted from the Earth, like reflected sunlight. NOAA scientists keep tabs on the sea surface temperature around the globe with a sensor on a satellite that measures infrared radiation emitted from the ocean surface. Active sensors produce their own energy. An example is a light detection and ranging, or LiDAR, system, which produces a beam of light and measures the time it takes to go to an object and back to determine the distance. NOAA pilots fly aircraft with LiDAR systems on board to map our coastlines and chart depths of the nearshore waters. These missions track changes of the coastline over time, as well as provide vital data to reopen ports after hurricanes or tropical storms strike. Satellites can also be used to collect and relay information from sensors in remote locations, like a telemetry tag on a whale or sea turtle. In addition to tracking the animal's movements, these tags can collect data about the animal's behavior and environment, helping us develop programs for their conservation and protection. NOAA is an agency that enriches life through science. Remote sensing helps our scientists extend their reach from the surface of the sun to the depths of the ocean floor, as we work to keep the public informed of the changing environment around us.
Can you think of a new way we might be able to collect data through remote sensing? Let us know down in the comments section. And if you like this video, be sure to follow STEM 30 on Facebook and Twitter, and subscribe to the National Air and Space Museum's YouTube channel.
Okay, so that's remote sensing or GPS. So to continue, here are the use of remote sensing in GIS. Okay, remote sensing plays a crucial role in enhancing GIS capabilities by providing valuable data for spatial analysis. So here are common applications of remote sensing: land cover classification, environmental monitoring, disaster response, precision agriculture, and urban planning. Last time we have already discussed the following, in GIS. But to give you more idea on how RS is contributing here, in land cover classification, it identifies and maps out the different types of land cover. For example, forest area, residential area, agriculture area, okay, using a satellite imagery. So that's land cover classification using remote sensing. Okay. We also have here environmental monitoring. We track the changes in ecosystems. We track the changes in climate and natural resources over time. Okay. The third one is disaster response. We assess, or it assess, the impact of natural disasters and aiding in emergency response through satellite imagery. So dito makikita natin yung possible locations ng typhoon, ng hurricane, so that we can easily, or the government can easily respond no, in emergencies, no, through satellite imagery or aerial photography. Okay, the next one, the fourth one, is precision agriculture. No, it monitors the crops' health, soil conditions, land use. No, using remote sensing data. It could be a through satellite imagery or aerial photography. Okay, that's remote sensing and precision agriculture. The last one is urban planning. No, we analyze and plan urban areas based again on satellite imagery and aerial photography. No, so halimbawa, meron kang bakanting lote, padadaanan mo siya ng aircraft, makita mo yung kanyang mga yung kanyang yung terrain, yung topographic area niya, kung ano bang possible facility ang pwede ilagay dito na mag-grow into, for example, into a commercial area, into a institutional area, or into a educational area. Okay, so that's remote sensing applications in land cover, environmental monitoring, disaster response, precision agriculture, and urban planning. Again, to discuss more about remote sensing and GIS, let's watch this video. Okay.
Hello guys, how are you doing? I hope you're great. So today I'm going to give you an introduction to remote sensing from a geospatial view. Yeah, my name is Jesse, and then today I want to give you the basics of remote sensing. This is our first tutorial, this is our first lecture about remote sensing, and more are coming. Just subscribe to this channel, and then I'm going to be sharing educative stuff every day. And also don't forget to invite a friend to like this channel. So let us begin. So the definition of remote sensing. Yeah, remote sensing is the science and to some extent an art of acquiring information about the Earth's surface. Why is it a science? Because scientific principles are involved, such as transmission, radiation, absorbance, reflectance, and other principles. And then it is an art because while you are analyzing these images, you put in some bit of art. For example, during map making, during choosing colors, during analysis, you have to put in some art. So through sensing, that is done by the sensor does the sensing, it records the electromagnetic radiation, and then from there you can process that radiation, analyze it, and then extract useful information. I hope we're fine from here. Actually, the sun produces a broad range of the electromagnetic spectrum, but we are only able to detect blue, green, and red, and other small colors which we can see. So, but as an advantage remote sensing has over us, when you use these satellites, you can be able to detect light that we cannot see. So, as you can see, this is an image acquired by a satellite. This is Scotland. This is England and other countries. This is water, and then it was acquired from the sky, as you can see. Yeah. So why should we have remote sensing? Of course, if you want to observe things that you cannot see with your human eye, you should use remote sensing. For example, look at pollution levels in the atmosphere. You can't see that, you can't measure that, then you need remote sensing. Or in case you want to measure carbon dioxide in the atmosphere, can you look at that? No. Another example is if you want to map inaccessible regions, for example, look at volcanic eruptions, you can't go there. Look at a lake, you can't go there. Then you can use remote sensing. So if you want to do a project in the shortest period of time, and then you don't want to go in the field, you just need to get some satellite images, analyze them, and then you will be able to go. And then by so doing, you would have reduced on the costs. And then when you do precise mapping using remote sensing images, then the accuracy of your project would be very fine. And there are lots and lots of more advantages of using remote sensing, as we shall see in the course of this course. Yeah. So applications of remote sensing. Remote sensing can be used in very many areas in our daily life. So these are a few examples I've used, but then more and more and more. We cannot exhaust them, but however, through my lectures, I will help you to learn how you can use remote sensing to in our day-to-day life to do some of these applications. Yeah. So application number one is water quality management. Actually, this was my undergraduate thesis while I was studying at Makerere University, and then I was using remote sensing to come up with a model that can be used to measure the amount of chlorophyll air concentration on Lake Victoria. And as you can see, this was one of my outputs. This is a map which was showing Lake Victoria's trophic status. Where you see this, these were highly polluted waters, and then where you see this, these were eutrophic waters, and that is one application of remote sensing. And then another application is land cover mapping. So this is a project I also did to compare the change in land cover in 1995 of this sub-county with that of 2016. As you can see, this is water, and then from seeing just visually, you are seeing that the urban areas increased more. This is an urban area, and then these are urban areas which were distributed throughout the image. And then you can see that the wetland reduced because this was a wetland, this was a wetland, and then you can see a reduction in the wetland. Also, more and more information can be gotten when you do land cover mapping using satellite images. So this is fire mapping, also it can be done. This is urban growth mapping, it can also be done using satellite imagery. So this is deforestation in Brazil. So this is an image in 1975, this is an image in 1986, and then this is an image in 1992. And then from seeing, you can see that the trees are reducing due to urbanization. Are you seeing urbanization encroaching on the trees? So with remote sensing, you can be able to study a given activity over a given period of time. This is called time series analysis, where you have different images at different time intervals and then you analyze them to get changes. And lots of which we cannot cover today, but through this series I'll share more and more and more with you. Just subscribe to this channel and then just make sure you watch every video I post. I want to assure you by the end of it, you'll be a very good remote sensing analyst. So let us continue. So how does it work? When we are doing remote sensing, one of the principles is the electromagnetic spectrum. Remember that electromagnetic energy is broken into different portions. So for example, we have the blue, the green band, the red band, the near infrared band, the thermal infrared band, the X band, the C band, L band, and the P band. However, these can further be grouped into the UV rays, the visible rays, the infrared rays, the microwave, and the radio waves. So for remote sensing, there is some part of remote sensing that takes place around here, another one here, and another one here, as you're going to see later. So the remote sensing process, yeah, this is what happens. We have a satellite, we have the Earth's surface, we have the sun, and then we have objects on the Earth. So this is actually passive remote sensing. When the sun is shining, it will send electromagnetic radiation to the Earth's surface. So when this radiation moves, it will hit the Earth's surface, and then it will move towards this satellite, which satellite will record this radiation. However, when it reaches the atmosphere, there are some form of interactions in the atmosphere. So some energy is absorbed, other is scattered, and then some of the energy reaches the what? The sensor. And that energy that reaches the sensor is the one that is recorded, calibrated, it is cleaned, it is stored, and then it is shared as an image. I hope that is fine with you. Yeah, this is just an introductory series. I wanted to start with this before diving into the waters. I hope that is fine. So we have passive remote sensing. With passive remote sensing, the only source of energy is the sun, and then without the sun, that means we cannot have any remote sensing that takes place, as you can see in that picture. And then we also have active remote sensing. With active remote sensing, the sensor can emit its own energy. It doesn't need the sun, it emits its own energy and then records it back. So an example is radar or LiDAR. With radar satellites, they will emit their own energy and then they record it back. I hope that is fine. Yeah. So I want to look at the sensor properties. We have spectral, radiometric, temporal, and then spectral resolution. So spatial resolution refers to the smallest possible feature that can be detected within a satellite imagery. Actually, it is what is represented by one pixel on the ground. Ideally, so if we have, say, Landsat 8, Landsat 8 has a spatial resolution of 30 meters. That means you can distinguish an object up to 30 meters. Below 30 meters, you cannot distinguish that object. And actually, if you are using it for mapping, you cannot map objects that cannot be seen below 30 meters. I hope that is fine. And then when we look at the resolution, we have coarse resolution. So this is a satellite image that is at a resolution of 5 kilometers. So that is very, very low. That is very, very coarse resolution. And as you can see, such resolution is used to map the world at a very, very bigger scale. But then we can also have a fine resolution. This is Washington National Airport, and this is 0.61 meter resolution. This is a quick bird image that was taken on December 2001. Yeah, and then as you can see, this is a very fine image. So that is the spatial resolution. When we have a coarse spatial resolution like this, then we can also have a fine spatial resolution. I hope that is fine. So we go to spectral resolution. So what is spectral resolution? Spectral resolution refers to the ability of the sensor to define fine wavelength intervals. What does that mean? In case we have a satellite that is able to record energy in narrow bands, then it has a very, very fine spectral resolution. On the other hand, if we have a satellite that has wide bands, then it has a very coarse spectral resolution. Yeah. So we also have radiometric resolution. And then radiometric resolution is just actually from common sense. It refers the number of bits used to store a given pixel. For example, we can have 8 bits and then 4 bits. So let me use this picture to demonstrate. This is a 4-bit image and this is an 8-bit image. So considering this image, are you seeing how you can get a contrast along this line? This is dark and then the color changes as you move this side. This is because they have used more and more energy levels to represent this image. So we go to temporal resolution. Temporal resolution refers, actually sometimes it is called revisit time. So it refers to the time a satellite takes to return to the same spot. So just imagine a satellite passes me here. How long will it take to find me again here? If a satellite passes Kampala, how long will it take it to come back to that same place in Kampala? So for MODIS, yeah, somebody's satellite passes in the morning and then another passes in the evening. Then for Landsat 8, it has a temporal resolution of 16 days. And then Sentinel-2A, it has a temporal resolution of 5 days. Every 5 days, you'll get an image. So how does temporal resolution help us? If you have a very high temporal resolution, that means you can get your images more often. Then that can be used to map abrupt changes and then daily changes. I hope that is fine. Yeah. So examples of sensors. We have the Landsat multispectral sensor that was launched in 1972 at a resolution of 80 meters. And then later, they brought the Landsat enhanced thematic mapper in 1982 at a resolution of 30 meters. There is Spot, there is Econos, there is QuickBird, there is ObView. There are very, very many sensors that are in the atmosphere that we can use for remote sensing. Yeah. So before I close this, I want to look at optical remote sensing. So remember, the electromagnetic spectrum is just a representation of energy levels. And then when you are dealing with optical remote sensing, you are just dealing with that remote sensing that takes place in the visible and then the near infrared regions of the electromagnetic spectrum, as you can see here on this image. I hope that is fine. Yeah, so when we are dealing with optical remote sensing, we have panchromatic sensors. These are sensors that are only sensitive to radiation within a given band, but this band can be broad. So to visualize it more, think of a sensor that records image but within one band. So such examples include Econos and then Econos panchromatic and then Spot HRV panchromatic. Yeah. So we can also have multispectral sensors. What are multispectral sensors? These are sensors which have a few more bands. Why am I saying a few more bands? They don't have a lot of bands, but they don't have a few bands. So it is a few more bands. So look at Landsat ATM or Landsat multispectral sensor. The number of bands they have, they are not small, but they are not very much. And then among all those bands, each band is specific to a given wavelength. For example, you have a blue, green, red, near infrared, thermal infrared, etc, etc, etc. And then we can also have hyperspectral sensors. Actually, the hyperspectral sensors acquire a lot of images in different bands. Look at a satellite that has multitude and multitude of bands. They can even stretch up to 100. So these ones are used in precise applications, e.g. crop health mapping, precise land cover mapping, etc, etc. Yeah. So, but then when you are doing optical remote sensing, one of the guiding principle, even soil, but then water reflects slow. So by interpreting this spectral curve, we can be able to map different materials on the Earth's surface. So for example, if I want to map vegetation, I'll take keen interest in the near infrared. But on the other hand, if I want to map water, I'll take keen interest around this band. I hope that is fine. Yeah. Thank you for watching. Before we dive into the software and all the tutorials, I wanted to give you a brief introduction